Did you sit down, Mark? Hey Mark, what's up?
Hey, Aaron, Ashley, Eileen, and Daniel. I was just skating and I was trying to learn how to ollie higher.
What's an ollie?
Isn't it a skateboarding trick where you jump with the board?
Actually, yeah, it's a pretty neat trick that I've seen done a couple times. I can't believe you know what an ollie is. It's basically you push down with the back foot when you're on the board, then you jump up, making the board come up with you, level it off, and you come down with the board. It's really awesome.
That's exactly what it is, Daniel.
Yep.
My ollie is about half a meter right now. Now I'm trying to ollie 1 meter.
Well, you know how we can improve that is we've got to study the physical components of an ollie.
You know, I think we should check it up on the internet. Let's go, you guys.
Yeah, that's a great idea.
Let's do it. Let's do it.
Physics.
Alright, let's look this up. Yeah. Google.com. Ollie. Physics of ollie.
That one looks pretty neat. What's that one?
What
Try that one. Click on it.
Okay. Skateboard science. Hey guys,
Awesome.
check it out! I found this really neat site on exploratorium.edu about the ollie.
Perfect.
Article's called Skateboard Science.
Perfect, perfect. Let's use it.
What
Okay.
site
Good
is
enough?
it from again?
So after exploring that website, I think I've determined there's 3 forces acting on a skateboarder when he's just skating along. We have total combined weight of the skateboarder, so mass times gravity, plus the combined weight of the skateboard, which is mass times gravity as well. So in this picture, we're just going to call it weight, total weight. The third force acting on the skateboarder is the force of the earth pushing up, which of course is going to be our normal force. But I don't quite understand how we get from skating along a flat plane to jumping in the air and looking like the board sticks to your feet like magic. Can you explain that to me?
Okay, I'll help you, Aaron. Well, what Mark needs to do is crouch down so that he lowers the center of gravity and the force is able to exert on the ground so that he can perform the trick. What happens is Mark's rear foot right here is supposed to exert a force on the tail end of the board that has to be greater than the front end of the board. And according to Newton's third law of motion, every action has an equal and opposite reaction, which means as Mark presses down on the tail end of the board exerts a force on the ground, and the ground exerts a force back upward that's equal and opposite to Mark, which enables him to actually jump up. This is demonstrated in the diagram shown here in the free body diagram, where normal force is indicated by the red arrow and the orange arrow indicates weight, which pretty much cancels out. But the new force, where Mark exerts a force onto the tail end of the board, the ground exerts a force vector going up this way, which is opposite in direction and same in magnitude.
Cool, so all I have to do is slide my front foot forward. The bottom of my shoe and the rough part of the board will drive the skateboard even higher. And it's the coolest part. When I push down on the front of the board, the back of the board will rise, and it will appear as if my feet are stuck to the board. Then gravity will pull me and my board down as we free fall to the ground.
So you know the conservation of energy is also included in this?
What's that?
So the conservation of energy states that energy is neither created nor destroyed, and so in an isolated system the energy remains constant. So right over here we have that initial kinetic energy plus initial potential energy equals final kinetic energy plus final potential energy. So as we substitute our values in, we get this equation, and we can rearrange that and manipulate it and we multiply it by 2 over m on both sides. And so the x component has an acceleration of 0, so the velocity is constant, which shows that x initial velocity would equal the x final velocity. And so at the highest point vertically, the velocity would equal 0, which means that the y final velocity is 0. So then we subtract the x component of velocity squared from both sides, and we result with this equation, which is initial velocity of y squared equals 2 times gravity times height. And so we substitute that in, so basically the y initial velocity is equal to v naught times sine times theta. So we can rearrange this equation and plug it in so we can come up with the equation to solve our problem. So basically 2 times gravity times height equals v naught squared times sine squared times theta, which is to isolate v naught squared by itself, we divide on both sides sine squared theta, and we result with this final equation, which is v naught squared equals 2 times gravity times height over sine squared times theta.
Alright, now right here, what this bottom portion of the poster board shows you is a little graph of the action of the ollie itself. Now as you see here, this is at the origin right here. You see the ollie takes off at a 45-degree angle and it accelerates upwardly. It gets slower and slower, the negative acceleration, up until it gets to the top of the ollie, which is when the acceleration equals 0. And after you're at that split second right at the top, you come right back down to hit the ground. All throughout, since the velocity is constant, you're going to have constant velocity all throughout. And at the top of the ollie, he's going to reach a height of 1 meter. Alright, so now that we've talked about all that, now Mark wants to know how he can get his ollie up to 1 meter. So basically what we'd have to do is to find out, first of all, what speed Mark would have to go at for his ollie to reach 1 meter when he takes off. So I'm gonna leave that question for you guys, see if you guys can figure that out, alright? Tick tock, 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 tick. Alright, so let's see how well you guys did right now. Now if you recall this equation that Eileen gave us earlier to find the initial velocity, you would have to go about plugging in the numbers of 9.8 meters per second squared, because that's the acceleration due to gravity, times 1 meter, because that's the height we're trying to achieve. And you divide that by sine squared of 45 degrees, because that's the angle at which we decided that you had to take off at to get that 1 meter. You calculate all that, and you come up with 6.8 meters per second. So if you got 6.8 meters per second, give yourself a high five, pat on the back, round of applause. I don't know. Reward yourself.
Wow! Based on that speed, how far do I have to travel?
Tick tock, 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 tick tock.
Time's up.
All right, time. Now, in order to find the distance, which we're trying to find r, we gotta first calculate. We gotta put in 6.8 squared, because that's what we got the first time. 6.8 meters per second squared. Multiply that by sine squared of 45 degrees, and we divide that by negative 9.8 meters per second squared, because that's the acceleration due to gravity. And we find that those numbers, we gotta go 5.5 meters to get the 1 meter height of the ollie. So if you got that answer, once again, give yourself a high five.
Yeah!
So check it out. First got it when he was 6, didn't know any tricks. Matter of fact, first time he got on it, he slipped, landed on his hip and busted his lip. For a week he had to talk with a list like this. Now we can end the story right here, but shorty didn't quit, it was something in the air. Yeah, he said it was something so appealing, he couldn't fight the feeling, something about it, he knew he couldn't doubt it, couldn't understand.
Site on explore20.edu about the ollie.
Perfect.
Article's called Skateboard Science.
Perfect. Let's use it.
Okay.
What site
Good
is
enough?
it from again?
Explore20.edu.
Good.
I can help you explain that, Aaron. Well, first of all, when...
Block 14 on
Does
this
it
column.
catch it if I do it the opposite way? Like back with my back facing it?
Yeah. Just try it both ways.
Was that in the picture?
Kinda, the second half of it.
I'll give you $20, dude. I swear.
Where's it? It's right here.
Now.
What if I piss off this rail and get all the way down there?
You're before it.
Huh?
You're right before it.
Right before it?
Yeah. It's like I see you land it, and that's it.
Oh, it's so good, too. But there's no consequences.
Like there. And that's where you land it, which is...
Put it on this block. Or actually, put it like right here.
Not the land, but I zoomed it out more.